Good afternoon, dear professors, students, and colleagues and friends. I'm Yao Hong from I'm a joint PhD student from Ghent University and Peking University. My supervisor in Ghent University is Professor Bart Mercy, and Professor Ce Jifu is my supervisor in Peking University. And the talk in today is the numerical implementation and analysis of a smart ventilation system for tunnel fire smoke control. I will introduce my topic from 5 chapters. First is the background, and the second is the method. Third one is the basic results, and the fourth one is adaptability of the proposed method. And the last one is the conclusion and the perspectives. First is the background. Because all of us are the students or professor related to the fires. So as you all know, the toxic smoke will be generated when a fire occurs. The fire can be extinguished if the firefighter can easily get close to the source of the fire. For example, if a fire occurs in the first floor in a room, the firefighter can break windows and put out the fire. However, if the space is narrow and long, in this case, the smoke will not rise or always induced by the buoyancy. So if a fire breaks out in a tunnel, the smoke will spread along the upstream and downstream of the tunnel. The high temperature smoke poses a great threat to people and properties whenever it goes. The bottom figures show the threat of the tunnel fires. We can see so much smoke will generate, and even it will be pushed out from the inlet or outlet of the tunnel. On the other side, the smoke greatly interferes with the line of sight and hinder the rescue of firefighters. Therefore, practically, the ventilation system is also used for the smoke control. Under the act of the longitudinal ventilation, the smoke will be pushed downstream. And if the smoke will be is controlled, is controlled at the fire source, then the smoke will not again hinder the rescue. So appropriate velocity can make the smoke just not spread upstream. This is the so-called critical velocity. At the right figure is showing at the bottom, if the smoke is controlled at the fire source, then the firefighter can be easily close to the fire source and distinguish the fire. How so far so many correlations is proposed by many scholars because this is a very important parameter. However, all of these correlations proposed by the scholars, they need if they want to know the critical velocity, they need to know the fire size, the tunnel dimensions, and the slope of the tunnel, so on. So many information. So this correlation is not suitable for this real fire scenarios. So in my study, we want to design a novel ventilation system that can adjust the ventilation volume or the ventilation velocity according to the information obtained in the tunnel. But the first question is how to capture the smoke movements information in the tunnel. Normally, we have two different detector or sensors in the tunnel. For example, the first type is the smoke detector, and the second one is the temperature sensor. However, the smoke detector can only give us the information about 1 or 0. For example, if the smoke detector detects the smoke, they can give us a signal of 1. But if they don't capture the smoke, and then can only give us information of 0. Although the smoke detector can give us the information very correctly, but they cannot give us a very specific information about the smoke concentration. The second type of is the temperature sensor. It's different because the temperature sensor can give us the specific value of the temperature. However, so we want to use the temperature information to capture and control the smoke. But they have a problem is how to control the smoke by control the temperature. Fortunately, we have the 2 physical facts about the smoke movement. The first is the Peclet number of the heat transfer. It's much less than 1. It means the convection dominates the diffusion for the heat transfer. And the second fact is the Peclet number of the mass transfer is also much less than 1. So it means the convection also dominates the diffusion for the mass transfer. So this means if you want to control the smoke, you just need to control the heat, because you want to control the mass, and but the mass and the heat is both is dominated by the convection. And for the tunnel fire, the convection mainly induced by 2 sides. The first is the forced convection. It's induced by the ventilation system. The second is the natural convection. It's induced by the temperature difference. So as the cartoon shows, we can see a sudden rise existed at the location of the smoke front. So as the smoke movement, so the location of the sudden rise also moves combines with the smoke. So let's zoom in the location of the sudden temperature rise. We can see at this location, the T1 to T2 is high temperature difference, but the difference of the 2 locations is very small. So if you can fix the temperature at between T1 to T2, and then if you can let the one location is fixed at the this temperature, so we can let the smoke front fix at this location. So then we can control the smoke front by controlling the temperature. As an example, if we put so many temperature sensor, beneath the ceiling, tunnel ceiling, and then the first, if we let the first sensor, which detects the highest temperature, then we can consider it as the fire source location. And then we can use this fire source used as the information for the for detect the smoke front. So this is the time series data is defined as the detected temperature. And then if we want to let this temperature close to the set temperature, this set temperature is in a range between T1 to T2, as previous mentioned. Go ahead. Yeah. 但是我按不了。OK。这个好像点不了。Remove what? Okay. Yes. So next step is we define the arrow function. It's equals to the detected temperature minus the set point temperature. We want set let this value close to 0. And then we use the automatic control algorithm, the PID controller, for control the ventilation system by the feedback of the arrow function. So finally, we can design this closed loop feedback control system. In this system, the feedback from the controller is the PID control algorithm. The full name is the proportional integral and derivative controller. And in order to prevent the inverse ventilation, we force it to be 0 if the value of get from the PID controller is less than 0. So in the closed loop feedback control system, the detected temperature is at the input of the arrow function. Then the arrow function is used as the input function to the PID controller. Then the PID controller can give us the ventilation velocity, and then we adjust the velocity according to its information. Then I will introduce how can the PID controller works for the controlling the smoke movements. If we only use the proportional controller, you can see if the smoke spread upstream too much, and then because the temperature is higher than the set point temperature, so the error function will very high. So the ventilation velocity increased as well because the error function is higher. But then after the ventilation velocity increased, the smoke will be pushed back downstream. After the smoke pushed back downstream, and then the error function will decrease as well. So the smoke will spread upstream again. So the system cannot be stable. It will wave around the fire source again and again. But if you add the second controller, is the integral controller. The integral controller can remember the history data, so it can know the previous information because it's give an integral of the error function. So now although the smoke will be also waved around the fire source, but each time it will be shorter for the backlinear length. So after the several rounds, the smoke can be stopped stable at the fire source. For the third controller is the derivative controller. This controller can speed up the stabilization time. If we add this controller, then it don't need to take so much time to be stable. It's just for one launch, then the smoke can stop at its position. So far, we only designed this smart ventilation system conceptually. So we want to implement this method by the simulation. In the simulation, we implemented it by the FDS source code. We coupled this PID controller algorithm into the safety source code. For the parts of the safety, we just don't need to change anything of the FDS code because we don't need to change any source term. But for each time step, we need to update the boundary condition. The boundary condition is updated by the PID controller, and the PID controller the input is the arrow function. The arrow function is extracted in the temperature field that calculated by the safety solver. So every time step, the detected temperature is updated. So this updated detected temperature can give the PID controllers this information how to adjust the ventilation velocity, and recycle this process and until the simulation time over than the maximum simulation time. And here we needed to do a technical detail. It's because the detected temperature in the large eddy simulation, maybe the value should be fluctuation, very nervous. So we need to smooth this curve of the detected temperature. We use this algorithm for smooth this value. You can say if you use this algorithm, the temperature curve, the nervous temperature curve will be smoother. And the next is the basic result of this method. You can check. Firstly, the most important thing is the stability of the system, because every automatic control system needs to be stable. If it cannot stable, then the system will be broken in the end. So in this test case, the hit rate is set is the 10 megawatt, and the tunnel hit width and length are respectively the 3 meters, 2.5 meters, and 16 meters. The detected sensor is put beneath the tunnel setting for 10 centimeter, and the control distance we set is 2.5 meter, and the boundary condition of the walls is the material of concrete, and the cell size of in the mesh is 0.0625 meter. It's much less than the D-star correcting. And the 3 parameters in the PID controller is this values. And the right side figure is the test result. We can see the hit rate, even we set is 10 megawatt, it still have some fluctuation, because in FDS, if we fix the hit rate, it's only fixed. The mass loss rate is fixed, and because of the EDC model, it still will have some fluctuation. And you can see the orange curve is the detected temperatures evolution. And you can see after the fire occurs, the temperature, the detected temperature will rise first, and then it's after the start up of the ventilation system, the smoke will be pushed back, and then the temperature decrease as well. And here you also defined the stabilization time by this equation. It will be useful in later. So we can see the system stable at around 50 seconds, but it's until the 400 seconds, it still is stable, the system. This is the contour of the inversion of the temperature field. We can see before the 21 seconds, the smoke still have some some smoke still cross over the detected location, but after 21 seconds, the smoke is controlled by the location of the sensors. The next important thing is to determine the parameters of the PID controller. Here, firstly, we need to do a estimation of the three parameters. For example, for the proportional controller, we need to estimate the KP. To estimate the KP, we need to do a magnitude analysis method analysis. Because during the control process, they have two stages. The first stage is the uncontrolled stage. In this stage, the temperature still have some rise and then decrease. And the second stage is the stable stage. The temperature just fluctuation a little. So in the uncontrolled stage, the KP should be in the order of V ventilation system or ventilation velocity over error function, because the ventilation velocity is in the order of 1, and the error function is in the order 10 square, because you can see in this curve the detected temperature is close, the maximum is close to 200. So finally, we can estimate the KP is in the order of 10 minus square. In the second stage, in the stable stage, now the ventilation velocity is also in the order of 1, but the error function now is decreased. It's only in the order of 10. But in this stage, the proportional controller cannot be the dominant term in the controller. So we only set the fluctuation is close to 10%. In summary, you can know the KP is in the order of 10 minus square. We use the similar analysis method. We can obtain the KI is in the order of 10 minus cube. And because of the stability of the system, we don't want and the system is turbulent, so we just set the KD equal to 0. And after the first estimation, next we need to do the optimization. We propose two methods for the optimization. The first is the trial and error method. We just test the KI now from the 0.005 to 0.02, and the KI varies from 0.001 to 0.006. And we test for the different parameters, and then we can get to the performance of these different parameters. The first very important performance metric is the X minimum. That X minimum is the smoke front that's supplied upstream. So the negative this number is equal to the backlining distance. So you can say as the increase with the KP and the increase with the KI, and the X minimum will increase, but we cannot increase the KI and KP too much, because as the automatic control theory, if the KI and KP and KD is too high, then the system cannot be stable. And the other, for example, for the stabilization time, it's also a very important performance metric. It means the how long it will let the smoke be controlled at the desired location we want to control. We can see the burst range of the K and KP is the KP can vary from 0.005 and the KI varies from 0.005 to 0.006. Overall, if we consider all of these performance metrics, we can obtain this optimized parameters. And then the second optimization method we proposed is to the system identification and genetic algorithm method. In this method, firstly, we need to modeling the plant model between a relationship, the detected temperature as a function of ventilation velocity. Normally, the system identification method choose the dead band and delay process. And we test the first order to the third order of this modeling, this model, and we fitted these models by at the sudden ventilation velocity at the 300 seconds after the fire occurs. So by fitting this curve, and we can know all of these three plant models, and we test this plant model with a triangle signal of the ventilation velocity. We can see the predicted curves also agree well with the real data. So for the simplification, we don't need to the second order and the third order. We just choose the first order because the three curves is very similar in the end. So after we get the plant model, we can optimize the PID controllers parameters by the genetic algorithm. We just need to give a step signal as the control objective for the PID controller, and then we use the PID controller's feedback as an input for the plant model, and then the control process we can get the evaluation metrics. Here we use this fitness function as the optimization objective. This means this function optimized in the genetic algorithm. For we created a generation, and this generation has so many individuals, and after the relative rotated well selection and crossover and mutation, and we then can get a new fitness. After so many rounds of the generation, we can get the near optimal solution of this problem. We test for a different number of pollution in one generation. Finally, even we use a different pollution for the algorithm, we can see the final value is converges. So after this optimization, we get another set of the parameters of the PID controller. We can see the KP is also in the order of 10 minus square, and the KI is also in the order of 10 minus 3 square, or 10 minus cube, and the KD is close to 0. It's very close to the estimation previously. So after the stability test and the parameter estimation, next time we just tune to test the adaptability of this proposed method. This demonstration is the one of the case we test in the simulation. We can see when the fire occurs, the smoke will spread upstream and downstream. But because the detected temperature is higher than the set point temperature, so the ventilation system will be start up, and then the smoke will be pushed back downstream and stopped at the fire source. But we can still see some fluctuation around the temperature sensor. But it's normal. Overall, it can stop at the location. And this figure is the ventilation velocity adjust in real time, the immersion. And then we test the adaptability for different heat release rates. In this test, the heat is fixed at 4 meters and the width fixed at 3 meters. And then the heat release rate varies from 500 kilowatts to 3,000 kilowatts. You can say all of these cases can reach to the stable stage in the end. But for the higher heat release rate, the average ventilation velocity is higher. This is the immersion of the ventilation velocity for the blue curve, and the green curve is the emissions of the smoke front upstream. You can see all of this case the smoke can be controlled at around the fire source. This is the location of the fire source. But the stabilization time is different. For the higher heat release rate, the smoke can be controlled faster. This is because for the higher heat release rate, the error function will be also higher. So the feedback to the PID controller will be stronger. So the ventilation also higher. This is some performance metrics of the results. The first is the maximum the DT. The DT is it's the smoke front in upstream. You can see all of these values is similar. It means the smoke, if before the smoke is controlled at the point we want to control, the smoke can spread upstream in a short distance. But as we know, for the higher heat release rate, the spread speed will be also higher. So it means the rise of the ventilation system also increase faster for the heat release rate, for the higher heat release rate. And the second metric is the time that the smoke reach to the maximum backplane length. You can see the this value is decreases with the heat release rate, just as mentioned above. And the third one is the average backplane distance is very close to the zero. It means during the quasi steady state, the smoke can stop at the around the fire source. The fourth one is the maximum detected temperature. It's saying that the temperature, this value increases with the heat release rate. It's very easy to understand because the higher heat release rate will lead to the higher temperature field. The fifth one metric is the variance of the backplane length. It's saying the the value is also very small. It means the smoke waves around the fire source is also have a small fluctuation. And this fluctuation decreases with the heat release rate. It's also because the higher heat release will give a stronger signal to the PID controller. The final one is the stabilization time. As discussed, it decreases with the HR as well. And the next step we need to compare the result with the experimental data. The first we can compare is the critical velocity. The critical velocity we now the most usual to use is the Li et al.'s correlation. In this correlation, if we give background length and heat release rate and other parameters, then it can give us a ventilation velocity. And in our design pro ventilation velocity, during the quasi steady state, we can also average the ventilation velocity. Then we compare this the critical velocity obtained by our method and the critical velocity obtained in the Li et al.'s experiment data. You can see the maximum relative error. It's around 23%. And the second experiment data we can comparing is the ventilation velocity at the maximum distance the smoke can spread. Because in this, when the smoke spread at the most far location, then it's can be considered as a stagnation of the smoke. In this state, the ventilation velocity can be seen as a very small short period of the stable state. So we also substitute this background length into this equation, and we can calculate the ventilation velocity by Li et al.'s correlation, and we can also investigate the ventilation velocity obtained by our our method. And after the comparison, you can find the maximum relative error is around 8%. The next, we test the adaptability for different tunnel dimensions. In this test, we fixed the heat release rate at 2,500 kilowatts, and the tunnel height varies from 3 meters to 5 meters, and the tunnel width varies from 3 to 4 meters. You can see for the tunnel height of 4 meters and 5 meters, the system can be very easy to identify at the stabilization state. But for the low tunnel height, the detected temperature similar. The curve is similar. It looks very nervous. This is because for the very low tunnel height, the sensor is very close to the fire source, so the temperature will change with high fluctuation. But interestingly, we can see even the immersion of the temperature is very nervous, but the smoke can also be controlled at the fire source. Finally, this reveals the strong adaptability for the proposed method. And we can see this is a top view of the temperature fields for different tunnel dimensions. You can see the tunnel heights strongly have strong influence on the temperature fields, but the tunnel widths don't have strong influence on the temperature distribution. The right side is the temperature distribution along the longitudinal direction, and you can also see the temperature distribution is strongly influenced by the height, but not the width. This result is also shows the almost every metrics is mostly influenced by the tunnel height, but not the tunnel width. And the average background length is close to 0 as well. It shows the good adaptability for the proposed method. And this is the comparison with the experimental data as the previous mentioned method. For the critical velocity, the maximum relative relative error is around 8.59, and for the ventilation that reaches to the maximum background length, the maximum error relative error is around to 5.53%. And the next adaptability test is on the time value heterogeneous rate. And the black curve is the heterogeneous rate curve that tested by the Elhemir on his paper fire test, on his book test of a single office workstation. Under the time value heterogeneous rate, you can see this pink curve is the detected temperatures evolution. Thus the curve cannot stable anymore. It's varies at any time. So the green curve that is the ventilation velocity is also varies always in the full period. But interesting is the smoke front. The blue curve can be controlled. It's very stable after the 6 seconds. So it's again shows the strong adaptability of the control method. The next is the adaptability test on the any desired locations. If we put the temperature sensor at a different location, we just to see if it can control as well. This figure is we test from with the control distance from 5 meters to 22.5 meters. You can see at the time of 31 seconds, only the A and ABC can be controlled, but the D2H cannot be controlled. But at the 100 seconds, all of these cases can be controlled along the location we put the we desired. This cartoon shows the control process of this small control. And we found for the different tunnel, for the different desired control location, the delay time proportional to the control distance. This is because this means the fire smoke spread close to the spread speed close to a constant number. And we also found 3 different control modes for the different control distance. More detail you can see my paper. And we also do a comparison with the experiment data. Now we we calculate the average ventilation velocity during the quasi steady state, and then we compare this velocity with the correlation calculated by the Lee et al.'s correlation. we can see a greater agreement with these two sets data. Lastly is the conclusion and the perspectives. We designed automatic ventilation system and algorithm for a small control, and we proposed two methods for determination and optimization of the PID controller's parameters. And we numerically implement PID algorithm coupled by the CFD solver. And finally, we numerically analyze the control performance under different fire scenarios, such as the heat release rate, tunnel dimensions, and the time varying heat release rate, and the different design locations. All of this scenario, the smoke can be controlled well. In the future, we also would like to do some experiments for the proposed method, and we also want, because of the strong fluctuation of the ventilation velocity, so we also want to use the Internet of Things system to combine with the smoke detector for the 1 and 0 signal to let the ventilation velocity more stable. If we have still more time, we also want to do some instigate some application in other fire scenarios. Thank you very much for your attention and joining for this seminar. Thank you so much.